Greetings, gentle readers. May 19, 2026. Reading Foundations today with Ross Finlayson. Fellow Earthlings, what it is about is foundations, a theory of everything, always, and always everything. The idea that there is one good theory at least, and then that suffices. Then there's all such manners of ordinary theories of any sort of kind of common sense or abstract logic or any sort of account of then for the formal and programming and these sorts of accounts. It's all one theory is the idea. So the previous talk was about the Continuum Hypothesis and about the notions of the convolutional setting, and that's where the Continuum Hypothesis is in the one sense it's kind of abstract in the sense of that it doesn't have much connection to daily experience, say, for matters of experience and experiment that make for the great science that everybody has. So at the same time, what it affects to reflect upon is the very notion of numbers counting or growing and getting from one and saying, well, it's not that, so now we have two, and it's not that, and now we have three, and so on out to infinity, then has, well, are we counting or are we numbering? And that those kind of go back and forth. The notions of well-ordering and well-foundedness from axiomatic set theory, usually an Upser-Mellor-Fraenkel set theory, then making for the reasons why the great atlas of mathematical independence is to help allay the worries of otherwise these, as Erdős put it, the giant monsters of mathematical independence, since otherwise they would just make contradictions. It has that it's a wider, fuller dialectic, so then it's possible to just keep turning things over and to avoid being trapped in an inductive impasse, where it's is of a sort of counterintuitive reliance on linear inductive thinking, that this wider, fuller dialectic is always having made cases for both sides of an issue, so that thusly even as various judgments can be made in terms of either wider surrounds or as of the relation to any other given setting in a modal temporal relevance logic, that the account then for the deductive analysis and then the analytical bridges, which basically define what are superclassical results as by only being accessible, being related to something for mathematics like the geometric series or Zeno's arguments, or in Fourier-style analysis with regards to the account of Cesaro's summability after the Feher kernel and the Dirichlet kernel and Feher sums and these sorts of accounts, giving a reason why it's like this so, or the fundamental theorems of the calculus and these sorts of things. Then have that something like the inductive limit is really a deductive limit, because it's given a place and a setting where it can live, instead of just kind of having a guess, a stipulation, an assumption, an axiom with regards otherwise to these things. So it's figured that mathematics is discovered. It's a Platonistic view of things, and it's a strong mathematical Platonism. Only the objects of mathematics and all their perfection as they would be, straight lines, right angles, perfect circles, and these sorts of accounts, then makes for that the foundations is kind of a bit more drawn out, but eventually then for the stronger mathematical Platonism, a stronger logicist positivism, because it can only be accounts that can be relayed and even to be formalized, to be first uttered and articulated in natural language, and then for the disambiguation of quantifiers and so on, to help resolve the paradoxes of quantification, induction, infinity, identity, and continuity. That's the usual way of things here, and it has been for a long, long time. So the idea then that that's enduring, and also it's resistant to meddling, so that a theory can be constant, consistent, complete, and concrete, has that these are the requirements in desiderata for anything that would be calling itself foundations, vis-a-vis all these kind of pick them up and put them down theories that are means of entertainment or of the inspection and the examination and the testing of conjectures to make theorems. Then that's where here it's then overall kind of a potentialistic setting. The potential fields are the real fields, and then with regards to the classical and those being the real fields, that the account then is holistic, and then furthermore that is thorough, and these are the sorts of reasons why there is a theory that then everything kind of attains to, is that's truth. Well then, as from reading last time, this is a book from Hans Reichenbach called Philosophic Foundations of Quantum Mechanics. And so, kind of like people might associate Karl Popper with science and falsificationism, then some things with Reichenbach get associated with statistics and probability theory. And so usually then we put that aside and just say it's our statistical hypothesis. And as with regards to certain accounts of random distributions, and so then they're given particular prototypes like the normal distribution or the Gaussian called the bell curve, as it's shaped like a bell, and accounts have the central limit theorem and tests, students Fisher's t-test. These kind of accounts from what's called college statistics usually enough, or the introduction or first or second year of statistics. Then for probability theory, that being calculus based usually, so that the counting arguments which make for reasonings why for a given population having a sample space, that there are events, and then as of those we can determine, given we only have a statistic as of a sample, statistics being computed numbers off of samples, and then collected samples, that also being a sample, then for summary in statistics, and then ordering in statistics, for a great difference in between numbers and counting, and also for something like summary statistics and order statistics, and that's for time series data. That then the accounts of the statistical method and the scientific method are much alike. Statistical method has us basically test whether to reject the null hypothesis. It's like, well, we don't have any information, but this would imply that there is some information about a probability distribution of a random variable. With regards to the independent and identically distributed, that basically making for then the law of small numbers being a law of large numbers, that counting arguments make for what's giving the uniform expectations. And then for generating the estimators, after sample statistics, and the sample mean, for example, the sample variance vis-a-vis the true mean and the true variance of an unknown random distribution. Then gets into then the conditionals and these sorts of things, and with regards to bias and the accounts for like skew and heteroscedasticity, and the what we would call analysis of variance and multiple analysis of variance, analysis of covariance, relating to the convolutional setting covariance to variance, and these sorts of accounts. That then the statistical method is based upon whether or not to reject the null hypothesis. Similarly, the scientific method is whether or not to falsify the theory. It's like, well, we have a theory that's got nothing in it, and so it doesn't say much. But it happens the same way every day. And then so if we have another theory that says, well, when something is so applied, so hold, we can make it repeatably, observably, and falsifiably in this account, showing that otherwise the theory that would be in place is falsified, has that we never validate or verify or confirm so much the scientific theories, and we don't predict things with statistics, although estimators can give an estimate. It's not what we said that made it so. It just happens to be after the fact that it wasn't different. That in the more strict and formal and conscientious and thorough accounts of the statistical method and the scientific method, that otherwise than various ideals as they would be of having information or a theory, and thus having that lives in the space only of the theory and only of the contingency, not the real account. Because otherwise, that would be it's just not good probability theory and statistics, or science, as it's usually put. So this book is copyrighted in 1944 by the Regents of the University of California, renewed by Maria Reichenbach. And it's the Dover reprint from Hans Reichenbach, 1891 and 1953. So in this preface, the author describes the theory. Two great theoretical constructions have shaped the face of modern physics: the theory of relativity and theory of quanta. So here, these are called the premier theories. There's general relativity or relativity theory, and I would just say general relativity instead of just relativity theory, because here GR is first, and SR, special or restricted relativity, is second. It's local. So instead of the usual account these days where SRians, as I put it, people who adhere to special relativity, and that's their only pick them up and put them down kind of theory, that they would have that being having then the general relativity case was derived from it, instead it's the other way around. And then all it says is just it's a theory of relative motion. So the absolutes are otherwise in effect. And then there accounts for the cosmological constant. Space-time is curved, or whether it just kind of is, that just indicates that as things move, that the geodesy is constantly, instantaneously, everywhere evaluated. And then also that could be modeled by an orbifold, or that it's just matter-of-factly a way of saying is like, when it all works out, that would be ideal. And then the L principle, light speed being a constant, is the other kind of usual attachment to the theory. And then otherwise being Galilean, and after the laws of mechanics, so there was a severe abstraction to the mechanical reduction, and then the severe abstraction to the electronic or electrical reduction, the electronic for the electron theory of matter, and the measurement of the charge to mass ratio of an electron, and that defining all the atomic constants and these sorts of accounts. That the mechanics is basically what gives relativity theory its grounds for detailing aspects of nature in theory. Then the quantum mechanics is this other side of the theory and says, well, we got particle wave duality. There's, after Heisenberg uncertainty or certainty, there's particle wave duality. And so then that just means, well, does that mean it's discrete and is indeterministic and random? Well, that's a easy way to measure stuff. I mean, sometimes that's the only means available, because these particles are too small or too fast to otherwise make for an instrumentalist or operationalist interpretation of the physics of the thing be available. Yet it could be a continuous quantum theory. Here the idea is that it's a continuum mechanics all the way down, turtle is all the way down, and then that it's a continuous quantum theory. Turtles all the way down is a quote from a conference. Someone's trying to figure out, it's like, well, how do we found this problem of induction? It's like, well, it's on the back of a turtle, the world. It's like, well, that's got to stand on something. What does it stand on? And it's turtles all the way down. So historically, and that was either elephants, usually enough, or turtles, the idea being is just the account of making a discrete account of thing, a quantization of things, is just like imagining it atomically and infinitely small after the infinitely divisible, somehow yet infinitely divided. The idea being that there's complementary duals of the macro and the micro, and that's there in the middle. We are just in the middle of things, in the mesoscale. Then the idea then that turtles or quarks or superstrings, stringlets, then eventually to points for spaces and points in geometry is the usual account of relating matters of scale, and well, trying to remain fundamental and elementary in a theory like points. in geometry, just a location, dimensionless. It's somehow defined by all the coordinates that point to it in the dimensions. Turtles. So I was driving on the road yesterday, and as I was driving around this one bend or corner, then there was like a bump in the road. It's like, well, is that a rock in the road, or perhaps it's some piece of plastic or something like that, an obstacle in the road. Not very large, not much bigger than this book, but a little bit bigger. And so I drove around it, and I was like, and I hoped other people would too, because it was just sitting in the road. So I went and unloaded some of this stuff, and then I was driving back, and the bump had moved more across the road. It had walked across the road, for it was a turtle. So I went and I pulled over, and then I hopped out and got a bucket and ran back, because by then the turtle was just kind of hunkered in his shell, and I don't know how it had not been run over by this point. So I picked it up, and it wasn't squashed or anything like that, and put it in the bucket, and then just carried it, and then I was able to get it to somebody to take care of it, like the Fish and Game or something like that. I'm like, here, have this turtle. So they took care of it. But the idea is that that's just a creature in nature. But his turtle is all the way down. But it's like, how does the turtle cross the road? It's like, usually it just doesn't, And so these are the kinds of things. Anyways, reading then from Reichenbach here. Two great theoretical constructions have shaped the face of modern physics: the theory of relativity and the theory of quanta. First has been, on the whole, the discovery of one man, since the work of Albert Einstein has remained unparalleled by the contributions of others who, like Hendrik Anton Lorentz, came very close to the foundations of special relativity, or like Hermann Minkowski, determined the geometrical form of the theory. So there are lots and lots of different people who have all kinds of accounts that go into these kinds of things. Like Fitzgerald here, all the accounts of these F-Lorentzians, which have their own models of systems, whether it's absolute ether theory and everything else is relative, or in many ways making relativity theory. Here the doubly objective relativity theory is considered a way to make it so it's like, well, you have mathematical treatments of the relativity of motion and also space. And so now they're both absolute again, too, in the local. So really that's more about the different accounts of the local and the global. And so it's called near field and far field, about weak and strong energies, or high and low energies and weak and strong interactions, expressing why the running constants make so that otherwise for the linear and something that's a relation that keeps the conformal mapping, and the affine in transformations in geometrical all the way is actually, to me, make account the running constants have that there's the hyperbolic, in a sense, at the ends of otherwise the linear. And so when the author says it's a geometrical account to make of these things, it's kind of a fragment of a geometrical account, and then it's made into fragments of geometrical accounts. Basically, the Euclidean geometry and then the Riemannian geometry modeling a well or a spike of the things. That being kind of the idea that, well, it's when gravity is in a well, it's in a Riemannian geometry, because it all just kind of falls in vis-a-vis on a plane otherwise, or in just a plane space. It just kind of rests. And so, and then the idea of the Minkowski at space-time defining some dimensions and that having geometry, still yet that's very much Euclidean. So the authors here stated approbation and approval of Lorentz and Einstein and Minkowski. That's one way to establish perspective and projection, establishing perspective by various accounts of restriction and comprehension, and otherwise just kind of all the dimensions, and then correspondingly as those are refined or considered, 3 dimensions or 2 or 1, for examples, or 4, at giving like a room for motion of some of these other accounts when there are dynamics of the running constants, running constant being an oxymoron. Constants don't run, and run things that run are not constant. The idea that at the ends they do, it's asymptotic. Then has that to prevent this sort of fragmented view of the perspectives from having that the notion that perspective is the total for the point, local, global, and total. It gets into the Machian and these sorts of accounts as to why it is just kind of looking at the inverse of things, and then about as like diminishing returns compared to curves of supply and demand or something like that, or elasticity of demand. That the elastic and the running constants then help define why these accounts otherwise to be these great linear accounts and being so tractable, and then also being made so that the various accounts of the constructions and the expressions and the algebraic of the accounts of rotation and reflection and the convolutional setting and symmetries. So all these become invariant theory then. Invariant theory is meaning it's linear in these sorts of accounts, and then that has that. For the foundations of physics, these are particular perspectives, and they're signposts and they're successful, but they aren't complete. And furthermore, by having been restricted, the reductionism for reductionism cancellation, reductionism correction. The idea being, well, now we've been able to give ourselves addition formula and subtraction formula and product terms and differential forms, and they agree. Then that's reductionism truncation and reductionism approximation. Then on all these algebraic expressions, those are implicits that have then at the edges why this is there's room in the theory to say that these formalisms still hold, and then all what they say is so is only like to so, and then all the other effects of things like heft, mechanical heft, that spinning bodies as simply beyond momentum's account of it's the integral of inertia, or the Newtonian law of inverse square can make for these accounts like heft or the cue ball, that there's already room in the theory for these things to be. And indeed, it's just normally not understood, or it's been forgotten, that those implicits always exist. And that they're sometimes, besides usually being nominally negligible, they're nominally non-negligible. And so they're being always nominally non-zero. And so these are the sorts of accounts then as to why. Then otherwise, this reading from the author so far, back in 1944 or so, saying that it's like, this is our system of the world, has it there are others. And so when I made a comment about Reichenbach the other day, it was from reading in the Dictionary of the History of Science, this great book. It's like an encyclopedia. It's got many sections. It's a bit beyond a usual kind of a dictionary, just giving definitions for terms. The account of then for the theory of probability and the law of large numbers, meaning that it's like, well, back to probability theory and statistics, it says, well, if you take enough samples of something, you will get a good idea of what it is. And as you take more samples, it's going to be more like the true distribution. That being a fair law of large numbers. And it's after a law of small numbers, because the law of small numbers is just says, well, we have small numbers. They're small because there's a bigger one, and so on and so forth. So the induction and the counter-induction, the co-induction, making it like there is a law of large numbers, and then that will decimate or attenuate or make to dissipate anything away. Then there's this one here as well, that beyond that is the law of large numbers. There's a law of large numbers outside that. One that says, well, we can get a law of large numbers because it goes every which way. There are smaller numbers than there are negative numbers, or there are smaller numbers and there are accounts of oscillations and restitution. So at least three kinds of laws of large numbers, making for three kinds of limit theorems, because probability and statistics is almost entirely built from the ground up about the central limit theorem. The central limit theorem basically says, well, if it has a mean, the distribution, and you can make anything pretty much to do, then it has an account after enough samples and various accounts of standardization and normalization, the central limit theorem, and then being able to apply the usual accounts of student and Fisher and t-test with regards to confidence intervals and all these sorts of things. That, besides the central limit theorem, much like there are these different kinds of laws of large numbers, there's the central limit theorem, a uniformization limit theorem, which is most people ideas of thing. It's like it's random, it's fair, and any sample is as likely as any other. And then kind of a polar limit theorem, it says, well, anything that's got a mean also has not just one long tail, but two long tails. The idea of the long tail being is like, well, everything's going to look like a central limit theorem, but actually it totally just trails infinitely far off the long tail of the distribution. So that, and you can think of that again as kind of like a running constant. It's like, well, what's the constant that defines the difference between the ideal Gaussian normal distribution, the bell curve, and it's a notion that 1, 2, 3, 4, 5, 6, and 7 standard deviations are like is after from 0 being 50%, 65 or 85. It kind of varies which one of those is first, and then 90, 95, 99, dot dot dot, out into the nines. These standard deviations after the sample variance and these sorts of accounts and the sample mean and these sorts of things. That then the long tail is like, well, if you invert that so that then you have kind of two poles, like, well, is it farther out than what it would make? These are kind of example of running constant from something that's kind of just as the sigmoidal that makes like an exponential and falls off versus and then goes to 0. These are one that it slopes off and maintains on out all the way all the way out. So getting into probability theory and theory of distributions then is a number of different things, because it's one thing to look at like the probability distribution is like the heap of things. So for the cumulative distribution function vis-a-vis the probability mass function and probability density function, that one is an account that has just the area underneath, and the other account is like, well, how fast does it drop off? Two different things here related to the integral account and the differential account. So it's funny that counting arguments are basically an integral account, and where the accounts of motion and determine gradient and descent are mostly a differential account. And so then that gets into why there's reasons for making for things like conditional expectations, and I know this is a bit grasping, but Bayes' rule and conditional expectations, that being an account as after a law of small numbers, already built into then later the notion of discrete and continuous distributions, that the continuous distributions are described by calculus, vis-a-vis just counting arguments and the usual sampling with replacement and sampling without replacement. Here the idea is getting into then for the law of large numbers and what that's would mean for a theory of probability theory, why it's relevant to make for accounts of the integral differ in different integral, one about the differential, one about the integral, and then in terms of distributions, that would be as like the relations to the moment generating function and these sorts of things. Where one of the central dogmas of probability theory is that a distribution is defined by any of exactly one example of one of these, the CDF, the PDF, or the MGF. And so that's the function. It's just a distribution. And the reason why it's not just called a function is because that way it's kind of privy to probability theory and these sorts of things. Has that it's here, and then it's just something I'm going to look to study a bit more as to why the moment generating function and the CDF, the cumulative distribution function, and the probability density function, and I'll often get CDF and PDF mixed up, whether it's distribution or density. But the idea being that cumulative distribution function just says, okay, go between 0 and 1, that's where it is. And so you pick between 0 and 1, and that's where it is. And then probability distribution function says, okay, go across this line, wherever is whatever is underneath that line is how much area is that's more likely to show up. Making for these accounts of y, then you can say for the p.d.f and the c.d.f that there are ways to approach that dart throwing or pin the tail on the donkey in a sense would make it so that there's totally different accounts to get into why those are so, and in their treatments, usually always p.d.fs because they're analytical and their area underneath them equals 1, vis-a-vis the c.d.f that ranges between 0 and 1. Then for these moment generating functions is that also be considering a couple of different accounts of what functions or distributions would describe probability distributions, because then it's another way to look into the account of that the central dogma or the dogma of probability theory is that there are random variables with unknown distributions, and that distributions are defined by exactly and uniquely one of these, a p.d.f, a c.d.f, and an mgf. That every distribution has exactly one p.d.f, c.d.f, and mgf. So for that being just an account is like, well, whatever works, it can make for, then when it gets into like, well, what needs to be all formalized, made not just sensible, but fungible, and working in terms, and then tractable, including out to accounts of the approximations that can then work with large problems with limited resources, and these kinds of things. That's basically dogma after this sample space and the events and these kinds of things for probability and statistics, the theory. Then the idea is that there's also an account that the uniqueness of a p.d.f is not so for something that's kind of like a non-standard distribution. So when you think of the numbers 1 through infinity and picking a random number at uniform random. So the account of picking a random number that's mostly located near 1 is like a Poisson distribution, or various accounts of Bernoulli and saying is like, well, just flip a coin and the first time you get heads, quit. But every time you get tails, then add 1. And so you can pick a random number that theoretically could be as large as arbitrarily possible, although as unlikely as getting the same count of a coin toss, fair coin toss, that number of times, which is small and diminishingly small, vanishingly small. So then the idea is that, well, is there a uniform distribution over the unit interval, 0, 1? It's like pick a random number between 0 and 1. Every region in that, every neighborhood is as likely as any other neighborhood of the same magnitude, its length, being the result. And so that it gets into like the idea of these iota values and line rails. Is like, well, how can that be if it's going to be not just one distribution for a uniform distribution, but all the different uniform distributions for all the different possible sigma algebras, say, there's magnitudes. And so, well, then we could get into that as a non-standard case. But here the idea is for just picking an integer at random from the natural integers at uniform random. So the idea is then this equivalency function, the idea being, well, we have a function that takes the numbers between 0 and infinity to 0 to 1. It basically just shrinks 0 and infinity into 0 and 1. And also, it's funny because when it's a discrete function, so you wouldn't expect it to be integrable according to calculus, yet it is. And it's also funny because also its area equals 1 under that instead of 1/2. You figure it'd be like, it looked kind of like a triangle because, as it goes from 0 to 1, that would be just like a triangle. But after these accounts of doubling spaces and doubling measures and having spaces and having measures, since Zeno, the bees flights or the wind sprinters, but here after Vitali and Hausdorff and equi-decomposability of these sorts of accounts, it equals 1. So that gives it a definition as a p.d.f. It is. I mean, that's what defines. Well, it's a distribution with area 1. There you go. It's a p.d.f. of something. And then similarly, as it goes from 0 to 1, and thusly, it's also a CDF. So it's a function that's both CDF and a PDF, or distribution, you could call it, or a functional. But here it's a function, a non-Cartesian function, or super-Cartesian. So that thusly, then the idea is like, well, if that's a distribution, what does it describe? It's like, well, what it describes is the natural numbers at uniform random. So it's as likely to pick as large a number as you can imagine as 1, or 3, or a billion. And then it gets some accounts like, well, is it basically 50-50 whether the number is finite or infinite? It's like, yeah, kind of. It's just arbitrarily large. The usual account is like, does it have a mean? Well, the answer is no. And these sorts of things. So it's uniform, yet as if for all the integers. So then the idea is like, well, if that's non-standard enough, then what's the point about the dogma of probability theory that thusly it's unique for that? Is that unique? It's like, well, not exactly, because you can kind of take the reverse of it, and that's also one, and also you can just kind of take it in the reverse and divide that by 2, and that's also a different function. But they all have the same property. They're all distributions of the natural numbers at uniform random. So it's kind of like these 3 laws of large numbers and 3 probability limit theorems. Now there's 3 distributions of the natural numbers at uniform random. And is that dogmatic? No, not exactly, no. But then furthermore, it's not really dogmatic in the usual accounts of the standard linear curriculum with regards to models of continuous domains, because here there's already 3 models of continuous domains: line reals, field reals, and signal reals, between the integer continuum and the long line continuum, all about only a linear continuum. Here's of interest. So then, and that gets involved with, well, then we can write all those as zeros and ones, and we're only talking about one of 2 things. We're talking about either the numbers between 0 and infinity, whole numbers, natural numbers, or the numbers between 0 and 1, real valued, all the numbers, the closed interval, their numbers as they would be between 0 and 1. So we can write all the numbers between 0 and 1 as a sequence of on-off bits, or zeros and ones. So like 0 is 0.000 ... ad infinitum, and 1 is like 0.111 ... ad infinitum, after the dual representation of these sequences. That equals 1.0 is 0.9999 ad infinitum equals 1.0. So then all those, possibly the whole world of those having a beginning and no end, it's called Cantor space. It's called 2 to the omega in the language of 2 to the omega. Then there are 3 models of those as well. There's one that's square and fits with these line reals, and there's the usual sparse one that fits with the field reals, the complete ordered field. Algebra's definition of, after Cauchy sequences and Cauchy-Weierstrass, giving a relation then for algebra and Cauchy and Weierstrass for delta epsilonics and analysis and arithmetic together. And then the signal reals, another account of all these samples in the reconstruction, kind of like sampling arguments in the small and providing information about a distribution. The notion of the signal theory and Shannon and Nyquist in reconstruction and perfect reconstruction. So the three of those as well. And they don't always exactly line up, like, well, this one is for the first continuous domain line rails, and this one is for the second continuous domain, the field rails, and this one is for the third continuous domain, the signal rails. But sometimes they do. And then for the things for like laws of large numbers, like, well, which law of large numbers would apply with regards to counting arguments, and then the integration and the differentiation of these accounts of the functions that describe these distributions, under what kind of conditions, as to how that would apply. Well, the idea is then that gets into the specifics and the particulars. And hear about all these other assumptions that have gone into making what are for counting arguments or classical probabilities. Like, you know that a six-sided dice has pips 1 through 6 on it, and if you roll it, then it's going to be uniform and random together. You can build counting arguments for 2 dice and 3 dice ad infinitum, ad absurdum, and ad infinitum. Then the idea here is that there's just this kind of wider perspective on spinning a wheel like a clock dial, and then just finding where it lands, as fine as that can possibly be measured, and then growing that ad infinitum until the space from which is sampling grows infinitely. So you can add more dice, or you can make a bigger dice, or a die. And so these are the accounts of what make for these different accounts of the things. So for probability theory and statistics, then, I haven't really got much yet into Reichenbach's account of quantum mechanics. Yet then the idea is that there are non-standard distributions and non-standard analysis about probability theory already in the field. You can search for non-standard probability theory and find a bunch of stuff that's going on in the field. I mean, it gets into why the probability theory got tired of other aspects of mathematics, saying their functions weren't functions. And so there's like, well, we're just talking about distributions only. And if we have a non-standard distribution, then we don't care that it's not a function, because we're not talking about that. Yet in the wider account, they are, they relate matters of relation and structural and all this kind of stuff. So then getting into a little bit more of this reading here, let's see what we can kind of gain from the idea of being that our law of large numbers has their plural laws of large numbers. It's not a pluralistic fragmented setting. It's just saying that due to various concerns of the space or the sampling, various large numbers, their laws are in effect. And it's not just the law of small numbers, and that would be the usual account here. And then for quantum theory, as this book is called Philosophic Foundations of Quantum Theory, then about things, there's been readings already from like Born and Feynman. So Born would have been before this, and Feynman would have been after this. And then the ideas and the accounts that make for why, since, as is called the Copenhagen Conference, and then for the Solvay Conference. But for Copenhagen, they said, okay, quantum mechanics is, it's of probability amplitudes. And so we can make a case for being able to sum these together, and that's still a distribution. So it says that distributions and a sum of distributions, just like the central limit theorem is built from just adding together these an infinite series that converges for the central limit theorem. It converges, the great derivation of the convergence of the central limit theorem. It's similarly so just for what they give as the account for probability theory is relation to statistics, to quantum mechanics, after statistical mechanics and the statistical ensemble, which is given first in its development for thermo second law, and then it was just kind of adapted to this setting, and then bringing in the Schrodinger picture after the Heisenberg picture. Yeah, I had a minor in statistics in my initial undergraduate, and so after about 15 credits, that's getting up to, ANOVA and ANCOVA and MANOVA and MANCOVA methods, techniques, and but not so much the theory. But then after getting a mathematics degree and then taking a probability theory, this is basically being like probability theory 301, the first lesson or something like that, the dogma of probability theory. Then having accounts already of like the non-standard, meaning the superstandard, is like, where's that going to fit? Is that it is quite central in this sorts of accounts. This theory, it is different with the theory of quanta, Reichenbach reads. This theory has been developed by the collaboration of a number of men, each of whom has contributed an essential part, and each of whom in his work has made use of the results of others. The necessity of such teamwork seems to be deeply rooted in the subject matter of quantum theory. In the first place, the development of this theory has been greatly dependent on the production of observational results and on the exactness of the numerical values obtained. Without the help of the army of experimenters who photographed spectral lines or watched the behavior of elementary particles by means of ingenious devices, it would have been impossible ever to carry through the theory of quanta, even after its foundations had been laid. In the second place, these foundations are very different in logical form from those of the theory of relativity. They have never had the form of one unifying principle, not even after the theory has been completed. They consist of a set of principles which, despite their mathematical elegance, do not possess the suggestive character of a principle which convinces us at first sight, as does the principle of relativity. And finally, they depart much further from the principles of classical physics than the theory of relativity ever did in its criticism of space and time. Their implications include, in addition to a transition from causal laws to probability laws, a revision of philosophical ideas about the existence of unobserved objects, even of the principles of logic, and reach down to the deepest fundamentals of the theory of knowledge. So, in the development of the theoretical form of quantum physics, we can distinguish four phases. The first phase is associated with the names of Max Planck, Albert Einstein, and Niels Bohr. Planck's introduction of the quanta in 1900s, followed by Einstein's extension of the quantum concept toward that of a needle radiation. The decisive step, however, so that would be like a spike, like Dirac delta spike. It's like, well, you know, Dirac delta is a spike, and it's infinitely tall and infinitesimally wide, yet it has area 0. It's like, well, imagine that being just like a needle, a tiny needle, and then you know these sort. It's an impulse type of thing. The decisive step, however, was made in Bohr's application of the quantum idea, the analysis of the structure of the atom, which led to a new world of physical discoveries. The second phase, which began in 1925, represents the work of a younger generation which had been trained in the physics of Planck, Einstein, and Bohr, started where the older ones had stopped. It is a most astonishing fact, this phase, which led up to quantum mechanics, began without a clear insight into what was actually being done. Louis de Broglie introduced waves as companions of particles. Ernst Schrödinger, guided by mathematical analogies with wave optics, discovered the two fundamental differential equations of quantum mechanics. Max Born, Werner Heisenberg, Pascual Jordan, and independently of this group, Paul A.M. Dirac, constructed the matrix of mechanics which seemed to defy any wave interpretation. This period represented an amazing triumph of mathematical technique which masterfully applied and, guided by a physical instinct more than by logical principles, determined the path of discovery of a theory which was able to embrace all observable data. All this was done in a very short time. By 1926, the mathematical shape of the new theory had become clear. The third phase followed immediately and consisted in the physical interpretation of the results obtained. Schrödinger showed the identity of wave mechanics and matrix mechanics. Born recognized the probability interpretation of the waves. Heisenberg saw that the mathematical mechanism of the theory involves an unsurmountable uncertainty of predictions and disturbance of the object by the measurement. And here once more, Bohr intervened in the work of the younger generation to show that the description of nature given by the theory was to leave open a specific ambiguity, which he formulated in his principle of complementarity. Well, that'd be something to look at some more as regards to the complementarity and Bohr's complementarity, because that's like the Machian, and it's also referencing the previously talked about the convolutive setting, the convolutive complementarity, and as why after unitarity and orthogonality, that these are then also the three groups. It applies to all these different theories because it makes for invariant theory all the surrounds of the things. That here's according to continuity law, vis-a-vis conservation law, and it kind of more expanded Emmy-Noether's theorem that a symmetry makes an invariant theory, makes a conservation law theory, that is continuity law. So here for Bohr to entertain this, we can well just say it's like, well, we're just making samples, and the sort of samples are statistical just by a matter of fact. Nature is still real, and so and the idea is that all of complementarity, orthogonality, and unitarity are always maintained, because in the great balance of all the things between the local and the global, of the point and total, it's worked out by philosophers of physics that is always to be so. And so all these various crises in physics are framed in one of those three breaking, and the other kind of tenuously holding, is the usual idea. Where the other idea would be that they all break the least amount at all, everywhere at once. All of them. The fourth phase continues up to the present day. It is filled with constant extensions of the results obtained toward further and further applications, including the application to new experimental results. These extensions are combined with mathematical refinements. In particular, the adaptation of the mathematical method to the postulates of relativity is in the foreground of the investigation. So, the relativistic quantum mechanics. We shall not speak of these problems here, since our inquiry is concerned with the logical foundations of the theory. It's with the phase of the physical interpretations that the novelty of the logical form of quantum mechanics was realized. Something had been achieved in this new theory which was contrary to traditional concepts of knowledge and reality. I would disagree with that, because it's infinitely small, and so the matters of the geometric mutations about length, space, time, and distance, with regards to the metric and norm, and matters of relative motion in the infinitely small, that being that it's always four turtles or something like that. And you don't know which one, but they end up making a stack on the way out, in metaphor, is that has a real explanation. So the notion that kind of like the notion that relativity says, oh, the fourth dimension, it means that anything is loose. They're no longer just like three dimensions. Everything has a place. There's a free dimension. So the fourth dimension in art and these ideas was basically just like, well, think outside the box. Then the notion of quantum mechanics is like, well, it's all indeterminate, has that every single part of it is determinate by itself. And then it's just a matter of sampling, and it's like, well, we can measure as many times as we want. Nature has already cut it once. And so that's the way of things. That it's although it's an entirely opposite view of the usual deterministic account, is anything goes, multiple worlds, and all this kind of thing. In theory, that's so, but in reality, that there's a system of the world. Freedom of will and freedom of consciousness, of course, is still given as unfalsifiable, that it doesn't exist. So that it still exists. While at the same, people still have personal responsibility and personal initiative. While at the same time, there is a system of the world, and then it's just accounts of reaching that make for all these regimes and extremes, the conditions of the configurations, the energy of experiment that make for the success of science. Based on the physical interpretations given, a philosophy for common use was developed by the physicists, which spoke of the relation of subject and object, of pictures of reality, which must remain vague and unsatisfactory, of operationalism, which is satisfied when observational predictions are correctly made, and renounces interpretations as unnecessary ballast. Such concepts may appear useful for the purpose of carrying on the merely technical work of the physicist, or the computer. But it seems to us that the physicist, whenever he tried to be conscious of what he did, could not help feeling a little uneasy with his philosophy. He then became aware that he was walking, so to speak, on the thin ice of a superficially frozen lake, and he realized he might slip and break through at any moment. It was this feeling of uneasiness which led the author to attempt a philosophical analysis of the foundations of quantum mechanics. Fully aware that philosophy should not try to construct physical results. Here it's so. There's just a strong mathematical universe hypothesis. That's a goal, actually. Nor try to prevent physicists from finding results. Right. That's agreeable. I mean, anybody can make of objects of mathematics, not whatever they will, but whatever they are that they will. He nonetheless believed that a logical analysis of physics which did not use vague concepts and unfair excuses was possible. The philosophy of physics should be as neat and clear as physics itself, should not take refuge in conceptions of speculative philosophy which must appear outmoded in the age of empiricism, or they don't. We still have an ideological tradition here, an idealistic tradition. Nor use the operational form of empiricism as a way to evade problems of the logic interpretation. So we're also analytic in this sense. We have both the idealistic and the analytic traditions, and kind of the best of. Directed by this principle, the author has tried in the present book to develop a philosophical interpretation of quantum mechanics which is free from metaphysics. It allows us to consider quantum mechanical results as statements about an atomic world, as real as the ordinary physical world. Oh yeah, the idea is and it's all real. And then here are the ideas they count. There's like, well, it's the potential fields that are real fields. And so the extra local with regards to quantum mechanics, because points and particles in the local, it's like I can only be defined by myself and my nearest neighbors vis-a-vis the extra local. It's like we all live in a field. It's like the ring world is unstable, you know, or something like that. Not so much the sky is falling, but, you know, the earth is tilting or something. Gives for that. And that just means that the potentialistic fields are the real fields vis-a-vis the usual classical account by itself, which is like that's living in a vacuum in a box. The division of the book is so planned that the first part presents the general ideas on which quantum mechanics is based. This part therefore outlines our philosophical interpretation and summarizes its results. So, this is a pretty careful and generous reading. It reminds me of Werner Heisenberg's introduction to his book on atomic physics, that being much more classical, and just describing saying, hey, we have classical laws that describe our atomic physics. And then we get into, you know, the accounts of the super classical. And so here, Reichenbach is just giving pretty much kind of like later we'd read from D'Espagnac in his great book, Physics and Philosophy. That was read here quite a bit about the late 20th century account of whether operationalism and instrumentalism were or weren't just fictionalism and fallibilism after fictionalism, the nominalism. Has that there's accounts where they're not. There's accounts where they're realists accounts too. So we can be realist operationalists and realist instrumentalists and conscientious physicists and care about the interpretation. So the contents of this book then are about causal laws and probability laws, the probability distributions, principle of indeterminacy, the disturbance of the object by the observation. That's usually given an account is that is a physical interference. The determination of unobserved objects, waves and corpuscles, analysis of an interference experiment, exhaustive and restrictive interpretations. So this would be more of an exhaustive interpretation. Yet the idea is that eventually that's liberating because it gives a first-class account of what interpretation is. Then part two is this outlines of the mathematics of quantum mechanics, expansion of function in terms of an orthogonal set, geometrical interpretation in the function space, reversion and iteration of transformations, functions of several variables in the configuration space, derivations of Schrodinger's equation from de Broglie's principle. I'd say de Broglie, that's what we were taught, de Broglie or de Broglie. Operators, eigenfunctions, and eigenvalues of physical entities, so matrix mechanics, the Hamiltonian. The commutation rule, here is noted also, it's like the anti-commutative rule, the given addition and subtraction formula after reductionism, cancellation, and reductionism correction, making reductionism truncation and reductionism approximation. Operator matrices, when things get easy. Determination of the probability distributions, time dependent of the psi function, transformation of the state functions, observational determination of the psi function, mathematical theory of measurement, rules of probability and disturbance by the measurement, nature of probabilities and of statistical assemblages in quantum mechanics, assemblages. Part 3, interpretations, comparison of classical and quantum mechanical statistics, the corpuscle interpretation, impossibility of a chain structure. It's called the path integral. I can't imagine what else to be talking about the impossibility thereof of what connects the things. So connections in the path. The wave interpretation, observational language and quantum mechanical language, interpretation by restricted meaning, interpretation through a three-valued logic, rules of two and three-valued logic. See here, I'd probably be able, if I flip to the page and he's got material implication or some of these other fallacies of non-truly classical quasi-modal logic, then that makes room for, like, as Marina Smolian and Fitting the other day, the non-classical logics. It's like, what's non-classical logic? What's non-classical about it? It's like, well, you know how classical logic is supposed to be like true and false, and you know, one or the other. Well, non-classical logic is not classical logic, and so in a sense, the quasi-modal logic here is also not classical logic. suppression of causal anomalies through a three-valued logic. So that's about techniques and truncations, usually enough. Indeterminacy in the object language, the limitation of measurability. So that speaks to really the great account of what the thing is. It's like, can we measure it? What is the value of the measure? So it's all about the measure problem and measure and all these kinds of things. So this talk today was mostly about the dogma of probability theory and the relevance of a deconstructive account of the assumptions that go into that dogma and the interpretations thus get attached. That there's reasons then that by equipping mathematics with this super standard account, automatically equips probability theory with the means to get some sensibility, fungibility, tractability of why these things are so. Then thusly, also that gets directly into the interpretation of a physicist's view of physics, given that they're exhaustive or here thorough. Good day, gentle readers. Reading foundations today. Super probability.